Hey everybody, Graham Balachi here from Building Blocks for Modern Humans. Thank you for joining me once again. In this episode, we're going to be continuing our series on the modern energy sources that modern humans use to fuel their modern existence. This is one I'm genuinely excited to share. This is one that has roots in our culture. You may have seen it on an episode of The Simpsons where Homer goes to work at the nuclear power plant. Of course, it is nuclear energy or nuclear fuel. In particular, we're going to be focusing on uranium, which is the metal that we typically use for nuclear fuel. We're going to be discussing all of that. So this episode is for people who want to know what nuclear fuel is, what uranium is, what some of the other options for nuclear fuel is as well, how much of it we use, how we use it, where it comes from, some of the downsides to using it, and I'll even throw out some dark horses on the future of nuclear energy and what the different technologies and different fuels might be in the future. So if you've made it this far, please like and subscribe to this video. I would really appreciate it. Otherwise, let's get to it. All right, so what is nuclear fuel? What I first want to talk about is the difference between a nuclear reaction and a chemical reaction. When it came to the fossil fuels, so the coal, the oil, and the natural gas, these are fuels made up of the elements hydrogen and carbon. So these are relatively light elements that are formed together into different types of molecules that we call hydrocarbons because it's made up of hydrogen and carbons. When we burn those and it releases all that heat, what's really happening is the hydrogen and carbons are combining with oxygen. The hydrogen produces H2O, which is water. The carbon produces CO2, which is carbon dioxide. The reaction of going from those hydrocarbons into the relative oxides releases a lot of heat. But here's the thing. The carbon stays, when it goes through that reaction, it stays a carbon atom. The hydrogen atom stays a hydrogen atom. The oxygen atom stays as an oxygen atom. These things are not changing what elements they are. All that's happening is the electrons around the outside of the nucleus are rearranging themselves into more stable configurations and going from one molecule to a different one, and that releases a lot of energy. That's what burning things is. You're basically just combining with oxygen and forming different types of molecules, and that can release energy. Now, let's compare that to a nuclear reaction, which is what we're going to focus on in this video. In a nuclear reaction, you are literally changing what the elements are. So one atom will turn into a different type of atom. So forget about the molecules and the combination of the atoms. You are literally going into the nucleus of the atom where there's a certain amount of protons and neutrons, and you are changing that nucleus. It is a nuclear reaction. What's really cool about that is it releases so much energy when you do that you don't need nearly as many atoms to get as much energy out as you would from a chemical reaction. It's a totally different ballpark when it comes to energy release. So that's one of the great things about nuclear energy and why we're going to focus on it. So most nuclear energy today, in fact all nuclear energy today, comes from what's known as fission. And that is where you are taking a large nucleus and turning it into a smaller one or a bunch of smaller ones. You're splitting it up into smaller nuclei. Nuclei is the plural of nucleus. So what we typically do is go after the really heavy elements, and I'm going to talk about that next, because most of the time what we're looking at is uranium. So let's take a look at what uranium is. Okay, so here's our familiar periodic table of the elements. These are the building blocks of the physical universe right here. Just as a reminder, the number in the top left of each of these boxes, this is the atomic number. That's the number of protons in the nucleus. That determines which element it is. You can have varying amounts of neutrons, which are the other component in the nucleus, that have equal mass to the proton, and that it won't change what element it is. That's determined by the number of protons, but it does change the mass of the nucleus, and that's different isotopes, which we'll get into in just a moment. So we start with the light ones, hydrogen, helium. These are ones we're familiar with. Let's go all the way down to number 92, one of the big boys, which is uranium. This is a big, fat, heavy metal, and this is what we focus on when it comes to nuclear fission for the nuclear energy that we use here on planet Earth to produce electricity so far. So at number 92 here, we have uranium. As a dark horse, which I can touch upon later, we also have at number 90, thorium is another option. And I'm going to discuss the role of plutonium as well. But for now, let's take a closer look at uranium. So here's a photo I got off Wikipedia of uranium as a metal. You're not going to find it like this in nature, but this is what it looks like in its highly purified form as a pure metal. This yellow powder here is known as yellow cake, which is uranium oxide. It's a mixture of different oxides, usually U3O8. This is how uranium is bought and sold around the world. This form of uranium is the one that's processed into the actual nuclear fuel that's used in nuclear reactors. We're going to touch upon that a bit later. So here's an example of what the uranium-238 nucleus might look like. By 238, I mean this is the 238 isotope. So you'll see that there's 92 next to that U symbol, and that means the number of protons. That's what makes it uranium, is that it has 92 protons. That's always the case. But we can have varying amount of neutrons, which are the other color. You see the blue and the white. One of those is protons, one of those is neutrons. We can vary the amount of neutrons, and yet it remains uranium. In this particular case, 238 minus 92 is 146, which means that we have 92 protons and 146 neutrons, which adds up to 238, which is why we call this uranium-238. 238 in this case means atomic mass units. That's the combination of protons and neutrons. There's also uranium-235, 234 in nature, and we'll discuss that in just a moment. So uranium-238 is by far the most common isotope in nature of uranium. It is not the most important when it comes to nuclear energy, and we'll discuss that in just a second. But what I want to show you is that this uranium-238, this is another property of uranium, is actually radioactive. It's not totally stable the way it is. By that I mean it's so heavy that it spits off little particles and changes the identity of the nucleus. In this case, uranium spits off what's known as alpha radiation, which is spitting off alpha particles, which is really just little helium nuclei. We can see an animation of that now, which I got from the University of Oregon. This is an example of a natural nuclear reaction. We're starting with one type of nucleus, the uranium-238 nucleus, and it's turning into thorium-234 and helium-4. So this is known as radioactivity, and it's something to be concerned about, but it's actually, with a little bit of shielding, not something that's really all that dangerous in this particular example. This is just another characteristic of uranium I wanted to bring up because it is something we have to manage. So the information in this image is interesting. There's 3 circles. The circle at the top shows the isotope breakdown of natural uranium. You'll see that almost all of it, 99.2%, is uranium-238. Less than 1%, 0.72 they're saying here, is 235, and there's trace amounts of other isotopes, a notable one being 234. But these are the main players, 238 and 235. 235 is the most relevant when it comes to nuclear energy, and I'll explain that in just a bit, but that's the one you got to keep in mind. So in the nuclear industry, what people do is they mine, and we'll talk about the mining in a bit, natural uranium. And for the vast majority of nuclear reactors, we need to first enrich it in uranium-235. So that means it goes through a physical process where we reject 238 and increase the concentration of 235. So the middle circle here, you'll see low enriched uranium, LEU, which is less than 20% 235, which is typically for most reactors 3 to 5% uranium-235. If we want to make a bomb, which, hey, I don't want to make a bomb, but it has been done before, we go to highly enriched uranium, which can even be weapons grade, which can be almost entirely uranium-235. So this is why uranium-235 is so important. It is a fissile nucleus, meaning it can undergo fission, which is what we're talking about here. This is the source of nuclear energy. On the left, you'll see a lone neutron coming in. It's fired at a uranium-235 nucleus. The uranium-235 nucleus briefly absorbs that neutron and becomes uranium-236 because of the extra atomic mass unit. That makes it so unstable that it splits apart into 2 smaller nuclei, barium-144 on top, krypton-89 on the bottom. And the key here is that 3 neutrons also come out of this reaction. Those 3 neutrons can go on to hit other uranium-235 nuclei and cause fission again in a chain reaction. Controlling this chain reaction is how we access nuclear energy. This is the key to all of it. So this is why uranium-235 is so important. Uranium-238 can be used in a nuclear reactor as well, but it's a 2-step reaction in that we first have to turn it into plutonium, which is fissile. Plutonium-239 is fissile. I'll explain that in a bit more detail in a future part of this video. All right, so here we go. How much nuclear energy or nuclear fuel or uranium do we use? Here, we're back to our trusty IEA World Total Energy Supply. We've already gone over coal, oil, and natural gas. Those are the big kahunas when it comes to how much energy we use. But at 5%, we have nuclear. So it's a relatively small amount. And now let's take a look at the way in which we use nuclear. So here's the IEA's World Total Final Energy Consumption. So this is the form of energy that we actually consume it in as humans. And you'll notice nuclear is nowhere on this list. And that's because in almost every conceivable notion, we turn it all into electricity. So while it could be possible to use the energy off of a nuclear reaction directly, we typically use it to produce electricity and then consume the electricity instead. And that's, you know what, that's a really high value use for nuclear energy, and I got no issues with that. In the section on how we use nuclear energy, we'll talk about how that conversion takes place. All right, so let's talk about the actual physical amount of uranium we use each year. To generate that 5% of our total primary energy consumption, it works out to about 67,500 tons of uranium per year is required to produce that much energy for humanity. That might sound like a lot, but really for that much energy, it's not that much mass involved. Consider that coal, and we talked about coal in the coal video, is, okay, 30% of the energy we use globally, but it's 8 billion tons of coal that goes into that. So think about that. 67,500, call it 70,000, that's fine. Scale that up to 30% and you get 420,000 tons a year of uranium to produce what would theoretically be 30% of global energy if we were to scale it up to that amount. So what's really cool about uranium is that these nuclear reactions are incredibly energy dense. The amount of energy you get out of the amount of mass involved is immense, which is the greatest thing about nuclear energy. How do we use nuclear fuel? As previously discussed, we turn it all into electricity, or pretty much. And how do we do that? Well, it's very similar to how we turn fossil fuels into electricity. Say with coal or oil or natural gas, which is a little different, in most cases what we do is we burn it, we take that heat, we boil water, that steam gets all pressurized, and we run that through a steam turbine which spins, is connected to a generator, and produces electricity. In a nuclear power plant, it's very similar, but instead of burning a fossil fuel, we have this nuclear reaction. We are splitting uranium atoms apart, and that releases a whole bunch of energy, which includes heat that we can use to boil water, pressurize that water, and send it through a steam turbine to produce electricity in a very similar way. So all we're doing is changing out the source of the heat. And instead of a combustion reaction, it's a nuclear reaction. Okay, so here is a simple diagram of a typical nuclear power plant. This is how we turn nuclear reactions into electricity, which is for the benefit of all humanity. And really, at this level, it's pretty simple. On the left is the actual nuclear part. You see the nuclear reactor. It's controlled by control rods, which we can get into. This is where the uranium-235 fission and all the heat and energy is produced. There is a primary coolant in this reactor, and you can see that being pumped around, and that goes into a steam generator. A steam generator is a separate loop so that we can contain the radioactivity inside this containment structure, where steam is produced in an isolated water volume. This is where the heat transfer from the primary coolant, which is typically water as well, it's something called light water, which is normal water, it produces steam in a different loop, which then goes through the turbine, which spins and produces electricity. And on the right side, we have a very typical power plant setup. There's nothing special about this. So this is what's known as a pressurized water reactor, which is by far the most common type of nuclear reactor, nuclear power plant. And I'm going to briefly show you the breakdown of the different types of nuclear power plants and what they mean. Okay, so this chart I got from UXC. I took a course from them last year. They're one of the leading sources of information on the global nuclear fuel cycle. You can check them out in the link below. Basically, what this shows is that PWRs, which is the pressurized water reactors, these are 71% of the reactors worldwide. These are the ones that require uranium enrichment, the uranium-235 enrichment. There's a different kind called the pressurized heavy water reactor, the PHWR, and these come from Canada. This is what's known as the CANDU reactor, and these can actually run off of natural uranium. They don't require enrichment, and it's a little bit complicated, but basically the uranium-238 can absorb a neutron, and then it goes through a different type of radioactive decay, which eventually turns it into plutonium, and then the plutonium can absorb a neutron and split and release a lot of energy that way. So it's a bit of a 2 or 3 step reaction as opposed to one. But hey, that's only 11% of the reactors worldwide. The vast majority of them, including the BWR, boiling water reactor, and all these other ones, these require enrichment, which is why the industry as a whole does require uranium enrichment, the uranium 235. Okay, so this map I got from Reddit. It's a map of the different nuclear reactors that are in operation today worldwide. I'm going to be straight with you. I don't know if this is 100% accurate. Some of those numbers at the top don't look right to me, but this is just for illustrative purposes. I think it's basically correct. You can see that the eastern side of North America, Western Europe, parts of Russia, and Eastern Europe as well, and over there in China and Japan, these are the highest concentrations of nuclear reactors worldwide. There's a lot of room for expansion, though. Currently, we have 428 operating nuclear power plants in 32 countries worldwide, with 63 under construction in 18 different countries. So that shows that nuclear is already quite present worldwide, and we are expanding it further. Where does uranium come from? Ultimately, it came from a dying star that exploded, and in that explosion, a whole bunch of really heavy metals were produced, along with a bunch of other elements, and then that formed into another solar system, and our planet formed out of that and collected a whole bunch of stuff that makes up the complex planet Earth we have around us. But where do humans find uranium in particular today? Similar to any other metal, we mine it out of rocks. There are rocks that contain metals. In fact, most rocks contain metals. And so there are experts in the world that know how to, and mineral exploration teams that know how to go find rocks that contain uranium and find deposits of these rocks that have high enough concentrations of uranium that it's economical to extract it and process it into uranium that can be used for a nuclear fuel. We'll talk about how that nuclear fuel is made quite soon. So really, there's a few different ways to do this. There are your typical surface mining operations that might look like this. There are underground operations that might look like this, where the rocks are much deeper underground. And there's another way to do it, and this is done a lot in the nation of Kazakhstan by a company called Kazatomprom. And this is called in situ leaching, where instead of digging rocks out of the ground and then processing them further, what they do is inject a solution into a geological formation, and they collect that solution back, and it is leached uranium out of the ground. And now it's in this solution that you can process to produce uranium after that. So those are the big ways to do it. Let's take a look at where some of those production facilities are on planet Earth. So here's a map I found on Wikipedia showing the different uranium reserves worldwide. The darker colors show where there's a lot more uranium, the lighter colors show where there's less. The gray areas also might contain uranium deposits, they just haven't been found yet, so they haven't been converted into what's known as a reserve. You'll see that Australia's got a lot of uranium, Russia, parts of Asia, Canada has quite a bit, United States as well. There's a lot of uranium out there, we just have to produce it. I'll say too that in Canada, where I'm from, in northern Saskatchewan, we have, as far as I know, the highest grade uranium mines on the planet. So 500 or 1,000 parts per million might be normal for uranium mines in Australia or the United States. In Canada, we have up to 200,000 parts per million, so 20% uranium straight up. It's known as pitch blende. It's just almost uranium oxide just there in the ground. It's one of the reasons Canada has had so much nuclear research done as well, is because we just have had access to the raw materials. Just taking a look at the uranium production by country, you'll see that Kazakhstan with 45% totally dominates, and that's with the in situ leaching method. Canada, with the highest grade uranium mines, comes in at 9.71%, which is pretty decent, which just goes to show you, just because it's the highest grades doesn't necessarily mean it's the cheapest production. So this here is an image I got off Wikipedia, and it's going to show us all the different steps involved from taking uranium found in rocks all the way through what's known as the nuclear fuel cycle. This is a simplified version of that, but that's all we have time for today, and I think you'll get a lot of information out of this anyways. So starting down in the lower left here, this is uranium that is present in rocks. This is natural uranium. And then obviously the next step up is mining, and this is showing the various methods for doing that. So in situ leaching or the typical rock mining, and heap leach is just a method of getting the uranium out of the rocks. That's another way to do it. From there, we produce our yellow cake, which is U3O8 typically. And then that goes through a process called conversion. This is right before enrichment, where we increase the uranium-235 to 238 ratio, which is the fissile isotope of uranium. In conversion, we produce we produce typically a gas called uranium hexafluoride. So there's just a chemical reaction involved to produce this gas. And then this is put through a certain type of centrifuge, which separates the lighter uranium-235 atom from the heavier 238 atom, and we get that process of enrichment. Now remember, for pressurized heavy water reactors, the CANDUs, which is about 11% of them, we don't need enrichment. We can use natural uranium, but for the vast majority, we do. We do need the enrichment step. So this is showing that particular step. We take the enriched uranium and we follow it up to fuel fabrication. So here we take our uranium hexafluoride, which has been enriched in uranium-235, and we take that back to an oxide, but a different one, uranium dioxide, UO2. This gets formed into fuel pellets that look like this, which are then put into fuel rods and fuel assemblies that look like this. And this fuel assembly comes from a pressurized water reactor, your typical light water reactor that needs enriched uranium. That fresh UO2, that uranium dioxide, then goes into the reactor. We hit it with neutrons and we get that chain reaction going. We use that to boil water and we produce electricity. From there, the spent fuel is stored on site, but can then be reprocessed. And this is where it gets interesting. There still is uranium-235 present, so some of that reprocessed uranium goes back to conversion to be re-enriched to squeeze out the remaining uranium-235. You can also take the uranium-plutonium mixture. Remember, uranium-238 can, after being hit with neutrons, decay into plutonium, and that can be used in different types of reactors, so we can send that back to fuel fabrication, and obviously some of it is just going to be disposed of in long-term storage as well. All right, so what are the downsides to using nuclear energy? There's so many advantages, there had to be some downsides, right? Well, there have been nuclear accidents. I mean, this stuff is potent fuel. There have been things called meltdowns that can potentially occur. The biggest example, there was a whole television series about it. It was at Chernobyl. That was largely as a result of inferior, older design and just operational error. That's something that is very rare, and you'd almost have to do it on purpose at this point. It's not really going to happen in the future. Other things like Fukushima, well, maybe we shouldn't put nuclear power plants right next to fault lines that could produce a tsunami. I honestly think it wasn't as bad as it looked at Fukushima, but there's no question. We learn something every time these things happen. We're going to prevent these things from happening in the future. And overall, if you look at the amount of people that have died as a result of using nuclear energy versus the people who have died from pollution from using coal and oil and things like that, at least in some of their more traditional forms, nuclear actually comes off looking pretty safe overall. There is no such thing as a source of energy with no risk whatsoever. There's always going to be advantages and disadvantages, and I think you just have to make a smart decision while taking all the risks into account. I mean, what else can you do? I think this is something that can be managed. The next drawback is the spent fuel, also known as nuclear waste. This stuff can be toxic. It can be still radioactive. Some of the products of the fission reaction are quite radioactive themselves. This is something that has to be managed. Compared to the amount of energy produced, it's actually not that much material. We're able to store it on site at the nuclear facilities for the most part for decades at a time. These things do have to be managed for sometimes hundreds or even thousands of years. There's long-term geological storage that can occur. There's a whole field emerging on not necessarily treating it as waste, but looking at it as something valuable, because there's a lot of stuff in there that we can use for things like nuclear imaging, cancer treatments. So it's not necessarily complete waste. We could reprocess it further and not have to manage it all long-term necessarily. That is something we have to manage though, there's no question, but I think we can do it responsibly. Those are the main ones. The other ones you might look at is that it's really expensive, and it's one of those things where building a big nuclear power plant is expensive up front, but then it's a very reliable and relatively cheap source of energy long-term for electricity in particular. So I don't see this as a weakness. It's just you got to kind of make your big investment, and then you got something that can last decades and decades. In Ontario, we've had this stuff rocking for like 60 years, and it's actually a pretty affordable form of electricity. So those are the drawbacks. I think they can be managed. but I had to be honest with you, that's what it is. All right, so I promised you before closing out this video that I would give you some dark horse potential technologies for our nuclear future. So we've focused almost entirely on uranium fission because that's what you see around the world today, and it works great, and I'm a big fan of it the way it is. But of course, people are trying to make it better, and they're trying to innovate and do all sorts of different things. The big innovation, we already mentioned thorium, which is a bit of an innovation. It's another heavy atom that we'd split, and there's some advantages to that. Some people think it's overblown, but whatever. You could use thorium. That's a potential dark horse, but I don't consider it a real one. The one that would really be a game changer is, as opposed to fission, which is splitting apart big atoms, we take small atoms and we fuse them in a fusion reaction to produce slightly bigger atoms, and that releases an even greater amount of energy. That would be amazing. And so not only would we not have to mine uranium, if that worked and we could do it all over the place, so we wouldn't have to mine for uranium. You could use things like hydrogen. That's actually what fuels the sun. In the sun, we're taking hydrogen atoms, which are just protons really, fusing them, we're not doing this, the sun's doing this, fusing them together to produce helium, which is, with 2 protons in the nucleus. That would be the next element up. And that releases all the energy that comes out of the sun, which we experience here on Earth as sunlight and heat and warmth and the life-giving nature that the sun provides for us. So that is a fusion reaction. So of course scientists are trying to harness fusion reactions here on Earth to produce what would be like virtually unlimited, near emission-free energy. Because think about it, the products from the sun is helium. Helium is not a dangerous substance at all. Even if you had to make something heavier, like helium plus hydrogen is lithium, it wouldn't be a big deal, totally manageable, and there wouldn't really be that much of it in general. That is the holy grail of energy production, is this fusion reaction. The problem is, the experiments we've done on Earth where we've been able to ignite some types of fusion, it takes more energy to put into it than we get out of it for the most part. Every once in a while you see it in the news that they've had some kind of breakthrough, but then it sort of quiets down. Operational fusion reactors that would produce net gain energy in a safe and economical manner have been one of those things where scientists are saying it's 20 years away for the last 70 years. There's always something that gets in the way of it. But if we could do that, and there's a whole bunch of people trying in the world, there's people trying in Burnaby, BC, General Fusion, there's people in France trying it, there's people all over the world trying this. Down in California, I heard about a company that had a breakthrough recently, or maybe it was at a university. Here's the thing though, if we could do it, it would be incredible, but it hasn't been done yet. But if we could, that would change everything. That's the major dark horse. The other one is, for fission reactions, instead of a solid fuel, like the fuel pellets I showed you, you could use a liquid fuel. And what's cool about that, there are some advantages to it, where the fuel, as it gets warmer, it expands, and that expansion actually cools it down and causes the reaction to calm down. And so you get this dynamically stable system where the temperature and the reaction rates find an equilibrium that can be quite safe. There's a lot of companies working on that right now as well. That's another dark horse. So that's it. As always, thank you for joining me. This is great. We're next going to look into, I'm going to probably do a combined video on renewable energy, the different types of renewables. So we'll take a look at that. That's the final piece of the energy pie that we've been looking at for this entire series. So again, if you'd like to, please like this video and subscribe to this channel, and I'll see you next time. Thank you so much.